This is the first of several spectroscopic techniques that we're going to be talking about in organic chemistry that have everything to do with determining structure for organic molecules. Obviously, the structure is going to dictate the function of different molecules, and that's something that we're going to see all throughout organic chemistry, biochemistry, molecular biology, all the stuff that you guys have in your very near future. But what we're going to do is we're going to talk about kind of the products of nuclear magnetic resonance, in this case, NMR, and we're going to concentrate on a very particular nucleus, which is C13, which is a particular isotope of carbon. The theory is going to kind of wait until later. First, I just kind of wanted to show you how NMR works in terms of the symmetry of molecules. And so what you're going to see is me holding up a lot of different structures that are model kits. This is one of those things, and it's one of many things in organic chemistry that will be made a lot easier if you guys have access to some sort of model kit. So the way that we're going to learn about C13 NMR is we're going to go through each one of the handouts, and I'm going to give you enough information to answer the questions on the handout without actually giving you all the information. And then later on in this, we'll actually talk about the theory behind C13 NMR. And honestly, like kind of the physical basis behind it doesn't matter as much to us as chemists as it might to like a physicist or something like that. We just care about the kind of being able to determine organic structures from the look of spectra, or to match organic structures to spectra. So with that being said, the first thing we're going to talk about is ethane and a couple of different kind of symmetry patterns in ethane that should allow you to match the spectrum that's in handout 1, which should appear right here. So what I have here is a model of ethane. You should notice that it's got 2 carbons and 6 hydrogens. It's the molecular model of the structure that's given to you in handout number 1. And you'll notice that I arranged it in a really particular way. So we're going to talk a lot about conformations of ethane, but what you'll notice is that I made sure that all those hydrogens were eclipsed. I should mention that I haven't put little white spheres representing hydrogens on the end here. Because there's so many hydrogens, it's just easier to talk about things with a model kit that looks like this. So one of the things you'll notice is that there's a symmetry plane that bisects perfectly this molecule, right? And such that those hydrogens reflect into those hydrogens over there. So it turns out that the basis of C13, or actually the basis of all nuclear magnetic spectroscopies, has to do with finding equivalent atoms, right? And so in this case, we're talking about carbons. So that symmetry plane that said that proton, or H, is the same as that proton, or H, in terms of its chemical environment, turns out that same symmetry plane interrelates these two C13s, right? So those 2 carbons are said to be in the same environment. Therefore, they're both a unique kind of carbon. And in the NMR spectrum, something like this is going to show exactly 1 peak. And that peak is going to correspond to the magnetic resonance, which we'll talk about in a little bit, of that particular carbon. Right? These 2 carbons are the same. That's 1 carbon environment. Of course, in this particular lab, we're not talking about proton NMR, but it turns out that the same symmetry plane that relates these 2 also relates these 2 and relates these 2. And so what that means is that since all of these hydrogens are equivalent, you also would get 1 peak in the proton NMR, having to do with the fact that each one of these hydrogens is a symmetry equivalent, right? And so, by the way, other symmetry planes are going to play a role, not so much in this carbon one, but you can see that there's also a symmetry plane that kind of takes this thing and divides it in half. So it turns out that this is equivalent to that hydrogen, but that hydrogen is also equivalent to that hydrogen, which is equivalent to that hydrogen, yada, yada, yada. Eventually you recognize that there is 1 hydrogen type of environment and there's 1 carbon type of environment. This particular presentation will concentrate on the carbon side of things. As we build butane, you'll notice that the way that I've arranged this right now, the symmetry plane isn't very obvious. So the idea is, in real time, this molecule, because of these single bonds, is able to rotate around. Obviously, all of these bonds are rotating. And just the fact that you can get to the point where you have a symmetry plane in a really particular conformation, there's the symmetry plane, right, or one of them anyway, you can see that we've kind of got a symmetry plane that bisects the middle right here. And so now we have something that's going to show two peaks on the carbon NMR spectra having to do with the two types of carbon environments that we have. We are either a carbon that looks like this, which, by the way, via symmetry plane is the same as this over here, right? So those are going to both show the same peak in the NMR spectrum. And then you've got an entirely new type of carbon environment, which are these CH3s out at the end here. So these are going to show the same peak in the NMR. So overall, you'll end up with two peaks for something like butane. And keep in mind, all of this has to do with symmetry planes. So what you're going to do for the remainder of handout number 1 is I want you to figure out what spectra match each of the other two options there. I want you to kind of notice the pattern of lines, right? Notice that not all lines are on the exact same spot along the spectrum there. There's that horizontal axis that's measured in parts per million, and we'll explain exactly what that is in just a second. You should be able to figure out most of handout number 2 if you keep in mind that idea of symmetry planes having something to do with the number of carbon environments in something. The one that I did want to mention just really quick is that benzene, which I have pictured here, right? So this is what benzene looks like. When we write it, it looks like there's this alternating sequence of double bond, single bond, double bond, single bond, double bond, single bond around the ring. But keep in mind that idea of resonance that we talked about very recently, I think in the first week, that actually told us that this single bond and that double bond, right, they're kind of in a resonance hybrid with one another. So it turns out that these bonds are all equivalent. So don't let that screw you up when you're looking for symmetry planes. I actually think it's really helpful to think about a benzene, at least in NMR, as like a big giant donut, right? And so these double bonds and single bonds, right, they are actually equivalent. So in terms of finding symmetry planes, what you'll hopefully notice is that there's a symmetry plane here, 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 and what you'll notice is if you look at that all the carbons are equivalent, and also the hydrogens are equivalent as well, but we don't care about those because we're not talking about that yet. When you look at handout number 3, the whole job that you're going to have is to match certain structures with the spectra that they produce. And what you should notice is that all carbon environments are not equivalent. In fact, it really matters what you're bonded to in terms of your position on the scale. You'll notice those peaks, they tend to move on that horizontal axis, which is called the chemical shift axis. And so we'll talk about the theory of what's going on there, but it's important to recognize that different areas of that spectrum correspond to different carbon environments. In other words, if, for instance, I'm next to a ketone, I'm going to be in a very different spot along that axis than if I'm, let's say, next to some sort of alkyl group. So at the end of this video, this particular little segment of that video, you should understand just the basics behind the theory of NMR. And as I said, if you don't understand what I'm talking about right now, don't worry, you will. It's something that requires quite a bit of physics. So if you haven't had physics, it may make things a little bit more difficult. But I'll do my best to kind of give the stupid organic chemist way of understanding what's going on behind this nuclear magnetic resonance, which is NMR. So the first thing to know is that atoms are actually spinning, right? And the problem is that their spins are said to be quantized. So let's pretend that I'm a C13 nucleus. right? And that C13 just corresponds to a particular isotope of carbon, much like you learned about probably when you talked about like C14 dating and things like that. It's just a carbon with a certain number of neutrons, right? It turns out that this nucleus can either spin one way or the other way. And because it's quantized, that's the way that this thing lives. And it turns out that if you look at the spin states of carbon, they have two, right? I can either be a plus 1/2 spin or a minus 1/2 spin. The world of quantum mechanics is a really, really strange one. The science of small is really, really strange. And so if you have no history in physics, this may be a little bit surprising. And I don't blame you. Even Richard Feynman, who was one of the founders of quantum mechanics, said that if anybody says that they understand quantum mechanics, they're either crazy or lying. So take my word for it, the spin state of a C13 nucleus is one of two things. And what you should know is that all of this universe that is made up of a whole bunch of different carbon molecules, us being a big giant bag of walking, talking molecules, all the carbons there, the atoms are actually spinning in one of two states. It turns out that C13 is, we look at an NMR because that particular isotope happens to have just two spin states that appear really well on the spectra that we are going to be looking at, right? So we don't look at C14, we don't look at C12, right? But we look at C13. Which is actually a really unusual isotope of carbon, but the good news is that we can actually see it on the NMR. So, all that being said, right, the important thing to recognize is that you've got two different spin states. Turns out, in just normal conditions, those carbons, like let's say that I have 100 carbons, so even though I have a whole bunch more in a sample, it turns out, you know, approximately 50 are going to be spinning one way, approximately 50 are going to be spinning the other way. So there's really no difference in terms of the population of those two states until I throw those carbons in a big ass magnet, right? And that's what an NMR is. It's this gigantic superconducting magnet that's really, really strong. And it turns out, for some reason of physics we don't care about, is that those two spin states are said to be no longer degenerate. In other words, one spin state, let's say spin minus 1/2, tends to go down in potential energy, and the spin of plus 1/2 goes up in potential energy. And by the way, those the plus 1/2 and minus 1/2, even those are kind of arbitrary. So let's look at kind of like an energy diagram having to do with throwing something in a magnet, right? So I'll draw a picture of a big giant magnet here. That's what a magnet looks like. At least Yosemite Sam's magnet looked like that. So I just threw some sort of sample into this big giant magnet, and it turns out in that case, the carbons of a plus 1/2 and a minus 1/2 are in different spin states. So what I'm going to do is I'm going to make like a little energy diagram here, right? And so we're in some sort of big giant magnet, and I'm going to put, let's say, the minus 1/2 spin state on kind of the lower potential energy state, and then the plus 1/2 on the higher. And as you might expect, that the 50-50 mix is no longer going to be true. There's going to be a little bit more down at this lower potential energy state relative to the higher potential energy state, right? And so let's pretend that the energy difference is enough, let's say, to put, let's say, 70% of the carbons here and 30% of the carbons here, right? And so, you know, much like if I went and I stood up on that table, it's very likely that I'm going to fall off and crack my head open by going to a lower potential energy state. The same kind of thing is happening here, right? We've got more occupancy of this lower spin state relative to the higher spin state. And again, that only happens in a really, really strong magnetic field. So what is nuclear magnetic resonance measuring? Well, it turns out that if you hit something with exactly the right pulse, right, the exactly right energetic pulse such that you take something in this spin state and you promote it up to the higher spin state. That will only happen where you hit it with that exact quantized amount of energy, right? And what we're seeing in the NMR is the result of promoting things up to a higher potential energy state, right? And so that, this is no longer 30%. Let's say that it's 40% now. And then once you stop kind of hitting it with that pulse, you measure how much energy is given off, and the NMR can record that, right? And so that's literally the lines on those spectra that you see correspond to really particular energy differences between the spin states of carbons. This technique is so incredibly sensitive that horizontal axis that we see, it turns out that the position of that energetic resonance at a really particular point corresponds to a really small variation between these different energy states. And there's different things depending on your environment that will tend to make you either in one position on the spectrum or in another position on the spectrum. So there's certain things that I can do to a carbon's environment to, let's say, instead of having this be the energy gap, maybe I do something where, let's say I make a very, very, very small change such that I make that energy gap just a little bit greater, right, represented by that red arrow. And it turns out that a carbon in this kind of environment is going to appear differently than a carbon in this kind of environment. And that's really what we're seeing on that NMR spectrum. Those of you that have had physics, this actually happens, that change in spin state happens in the radio frequency range, which is not a very energetic kind of thing. It turns out electrons also will do this, but we don't usually use electron spin resonance very often in chemistry. That's more of a physics thing. But that's what gives rise to the position on that scale. That parts per million scale, by the way, it's not that important that you understand exactly what that means, but essentially it corresponds to different frequencies, different numbers of hertz, right, according to where that particular cycles per second is. And if you really care about this stuff, your book does a pretty good job of explaining NMR. And so I'd be more than willing to give that to you if it's something that interests you. But for us, all we care about is kind of understanding the peaks on the parts per million scale. So that's what I'm going to represent in just a second. I'll just kind of show you a little bit about why we care about carbon environments and what it'll do its position on the NMR scale. Okay, so now that we understand just a little bit of what's going on in an NMR spectrum, let's reproduce one of those spectra, and highlight a couple of things that you should definitely recognize. Okay, so this, you'll notice it's kind of a bizarre scale because the 0 is always on the far right of the scale, and at least in carbon, we go out to about 200 parts per million. And what I'm going to do is just kind of highlight a couple of different areas, like really broad brushstrokes in terms of areas that you guys should recognize. It turns out that this 0 parts per million corresponds to what's called the most upfield part of the spectrum. So that's probably a pretty important term for you to understand. When I say the word upfield in NMR, what it means is you're shifted very close to 0. And then, of course, the opposite of up, last I heard, was down. And so this is downfield. So 0 parts per million is something that you just, you zero out your NMR spectrum to. Usually it's tetramethylsilane, which is this like really, really shielded, electronically shielded nucleus. In other words, there's a whole bunch of electrons kind of surrounding the carbons in that thing that tend to put it really, really far upfield. It turns out anything you do to take away electron density from something, it turns out that you're going to tend to shift downfield. So upfield are the things that are not very close to something that's really electronegative, for instance. So let's just pick out just a random CH3 group in some sort of really boring alkane, right? So it turns out that a CH3 group usually runs on a carbon NMR right around 20 parts per million. And it turns out that if we were to put electronegative elements into that thing, right, to put it electronegative elements near the carbon, let's say I put an oxygen near that, it turns out that what's going to happen is that peak is going to be shifted downfield. So let's say we might shift it to there, to around 60 parts per million. That's going to be something that we're going to learn to recognize, right? We're going to be able to look at a spectrum and based on the position of peaks, kind of give an educated guess as to, oh, that's probably based on the molecular structure of something. That's probably where the oxygen is bound, right? That's the carbon that corresponds to that particular oxygen. And so as we look at this parts per million scale, there's a couple of areas that are going to become pretty important to us. And you can look at your correlation guide if you really want to, get some really good sleep tonight. This video is just about kind of getting us used to kind of recognizing certain trends. So what I would say is if you are just some sort of boring old carbon, right, that's not connected near anything very exciting, you're going to run kind of in this area here. If you have something that is very electronegative, it could end up in this kind of like 60 parts per million area. For some reasons that we'll probably never get into, the alkene carbons are going to tend to run like, let's say, around 120 ppm. Right? And so if we see a peak around 120, that's going to be some sort of an indication that we might have an alkene, right? And an alkene is a carbon that is double bonded to another carbon. This particular region right here, where it's like, let's say around 170 ppm, if we see peaks here, and by the way, usually there's a whole bunch of them, that's what's called the aromatic carbon area. So we're automatically assuming that whatever carbons are here are somehow associated with a benzene ring. And another really important area out near 200, let's say like 190, and again, this is all depends on the exact group you're talking about. This is where there's some sort of carbonyl very likely. So that's kind of what we're trying to get out of this, is that you guys kind of, tackle these different handouts, try to come up with some different suggested structures. I'll take a look at it, give you a little bit of advice. But one thing I will say is that NMR can really hurt your brain if you're a really type A person, because you try to figure out the exact position of everything and you're like, why is it over there? Well, it turns out there's a lot of complexity in these spectra that I'm kind of leaving out. So just kind of try to take broad brushstrokes out of this thing at this point, and understand a little bit of NMR theory and have some fun. Moving on to handout number 4, it's going to be really useful for you to look at the correlation chart. The correlation chart's a little overwhelming to look at this point, but what it's trying to summarize is approximately what areas of that parts per million axis, that horizontal axis, corresponds to really particular carbon environments. And so what you're asked to do in handout number 4 is to just come up with, first of all, the number of carbon peaks that you're going to see based on the number of equivalent carbons in those different structures, but then kind of to make a guess at approximately where those are going to be on the chemical shift axis according to the environments that the carbons are in. So give that one a try. Handout number 5 is where you're going to be asked to do something that you're regularly going to do in organic chemistry. And that is to take a spectrum. Generally, we're going to see, once we're at the end of like second term, we're going to know all the different spectroscopies and we'll end up with a bunch of different spectra that we're then able to like suggest a consistent structure. In this particular kind of beginning activity, what we're going to get is the molecular weight of a compound, which is going to allow us, based on the molecular table's molecular weights, to kind of figure out approximately what atoms are in a molecule. And then, based on that, to give some sort of structure, looking at both the chemical shift and the number of peaks in a spectrum. So give that one a try, and if you have questions, ask me. Handout number 6 is the one that's going to take the most time probably, and that's the one I dedicate a lot of time to over the course of this next week. And that's the one where your job is to figure out approximately what the molecular formula of something is, and then to match whatever you come up with the spectrum that is provided in the, I guess I'll just put it right here so that you can find it underneath the lab items there in week 2. And this is the closest to what we are eventually going to be able to do very easily. Well, I shouldn't say easily. We will be very effective at figuring out, based on the spectrum of something, we're going to be able to figure out a structure given a couple of other items of information. So give handout number 6 a try. It's very likely that if you have a model kit, it's going to be really, really helpful. If you don't, talk to me. I have a couple of kind of free online sites that you might be able to use.